Hello student, welcome to my channel Learn Physics. I have already discussed 9 one-shot video of class 12 from NCERT chapter 1 to chapter 9. These one-shot videos include theory and NCERT numericals of all topics. I hope this video will be extremely helpful in your board exam, main, NEET and advanced. Now today I will be discussing the one-shot video of chapter 10, the physical optics or wave optics. This chapter mainly 4 basic topics: Huygen's principle and related to this, interference, diffraction and polarization. So this video will be very interesting for you. Please like, share and comment on this, and if you are new, please subscribe my channel to get the better mark in your upcoming exam. Okay, let's start. First of all, wavefront. Suppose this is the point source. From this point source, light travels in all directions. Now, after 1 nanosecond, the distance traveled by light c into t, that is 3 into 10 to the power 8 into 10 to the power minus 9, that is 0.3 meter. So, after 1 nanosecond, the light travels same distance 0.3 meter in all directions. Therefore, the particle lies on the surface of a sphere of radius 0.3 meter. And their phase phi equal to 2 pi x, that is 0.3 divided by lambda, where lambda is the wavelength of the light. So from this condition, the wavefront is the locus of all points vibrating in phase. That is, phase difference between the 2 points of a wavefront is equal to 0. Now look at this ray. Ray is the normal to the wavefront. Look at this is the ray, this is the ray, this is the ray, this is the ray, and this is the wavefront. So ray is always normal to the wavefront. Depending on the shape of the source, wavefronts are of 3 types. Number 1, for point source, it is the spherical wavefront. Now look at this for linear source. Linear source, look at this. Linear source, from linear source, light travels in all directions and vibration lies on the surface of a cylinder. So they produce cylindrical wavefront. Now look at this. This is the ray. This is the ray. This is the ray. So rays are always normal to the wavefront. Look at this. This is the ray. This is the ray. And rays are normal to the wavefront. Now plane wavefront. Very small portion of a spherical or cylindrical wavefront produced by a distant source. It appears like a plane. Look at this. It appears like a plane called plane wavefront. Okay, look at this. This is the plane wavefront, and this are the rays. Okay, now a question. Now look at this. This is a plane wavefront. This is a plane wavefront, and this is also plane wavefront. This plane wavefront incident on the prism. What is the shape of the wavefront after refraction? Shape of the wavefront after refraction by the lens, and shape of the wavefront after reflection by a concave mirror. Now look at this. We know the parallel rays incident on the prism. After refraction, it bends towards the base, and rays becomes parallel. Look at this. So the refracted wavefront becomes plane and it inclines this angle, because this line is perpendicular to this and this. So this is the refracted wavefront. This is the A dash, B dash. Okay. Now in the same way, look at this. Any parallel rays incident on the lens are meet at its focus. So look at this. The nature of the wavefront with the spherical like this. Okay. So look at this. This is the C dash, D dash. Now look at this. The parallel rays incident on the concave mirror meet at its focus. So look at this, the nature of the wavefront becomes spherical and like this. So this is the E dash F dash. Okay, understood? Now next. Now ncert 10.2. Now look at this, this is a point source. The ray diverges from this point. We have to draw the shape of the wavefront. Now look at this, if a perpendicular line is drawn, this and this ray, so this represents a sphere. Therefore, nature of the wavefront of diverging ray coming from a point is spherical. Now look at this, this is a convex lens. A point source is placed at the focus of the lens. So after refraction, the rays becomes parallel. Now parallel ray forms a plane wavefront. Okay, so nature of the wavefront becomes plane. Okay, now next see the portion of wavefront coming from a star intercepted by the earth. Stars are heavenly body, so they are infinite distance from the earth. The small portion of this wavefront appears like a plane, so it forms the plane wavefront. Okay, now propagation of light wave with the help of Huygen's theory. Okay, now AB is the part of a primary wavefront produced by it. According to Huygen's, each point of AB act as a secondary source called wavelet. Okay, so number 1 is wavelet. Number 2, each secondary source or wavelet send out light wave as same way as that of original source with same frequency and same speed. So look at this. So these secondary sources produce wavefront. Look at this. This is the wavefront. Okay. Now number 3. If envelope drawn from the front portion of the wavefront produced by secondary source represents the final position of the wavefront. So look at this, number 3 is the A dash B dash is the final positions of the wavefront. And number 4, there is no wavefront behind the line AB. Understood? Next. Now laws of reflection with the help of Huygen's principle. Look at this, this is the reflecting surface. Now look at this is two are incident rays. So they reflected in this way. Okay. Now look at this is the incident ray and this is the reflected ray. Okay. Now a line is drawn perpendicular to these two incident ray. So look at this is a line which perpendicular to both. We know the rays are normal to the wavefront. So look at this represents the incident wavefront. Look at this is the perpendicular and this also perpendicular. Now a normal is drawn here. If this is the angle of incident I, this is 90 minus I, so this is the I. Okay. Now a perpendicular line is drawn on these two rays. Look at this is perpendicular to this and this also perpendicular to this. So this represents the reflected wavefront. Suppose this is the DE. Okay, understood? Now a normal is drawn here. If this is the angle of refraction R, this is the 90 minus R, so this is the R. Okay, understood? Here incident wavefront perpendicular to the incident rays, reflected wavefront perpendicular to the reflected rays. Now from a wavelet at A takes same time to reach E as time taken by a wavelet to reach from B to D. Suppose this time is T, therefore look at this, AE equal to BD is equal to C into T. Now from triangle, look at this, from triangle ABD. From this triangle, sine I equal to perpendicular by hypotenuse. So look at this, here BD is the perpendicular by AD is the hypotenuse. Now look at this, BD equal to AE. So look at this, this becomes AE divided by AD. Now from this triangle, look at this, from triangle AED, AE by AD, perpendicular by hypotenuse, this equal to sine R. Understood? So this is the sine R. Therefore sine I equal to sine R. Therefore I equal to R. That is, angle of incidence is equal to angle of reflection. Now first law of reflection, look at this. Suppose this is the A dash. So A dash incident ray, AN normal, and AE reflected ray are on the plane of the board. So they are coplanar. Understood? Next. Now laws of refraction with the help of Huygen's principle. Look at this. This is the surface of separation of two medium where velocity of light c1 and here velocity of c2. Here c2 less than c1. That means this is the denser medium and this is the rarer medium. So Ri of this medium with respect to this is the 1 mu 2 is equal to c1 by c2. Velocity of light in this medium divided by velocity of light in this medium. Okay, understood? Now look at this. Look at these two parallel rays incident on this surface. Now a perpendicular line drawn on this rays and this rays. Look at this. This is the perpendicular line. So this perpendicular line represents the incident wavefront AB. This wavefront first incident at A and finally incident at the point D. Okay. Now look at this. The rays after refraction. Look at this. The rays after refraction moves along this direction. The rays after refraction moves along this direction. Okay. Now a perpendicular is drawn on this. Okay. This is the perpendicular. So look at this. Suppose this is the A. So D is perpendicular to this and perpendicular to this. So D represents a refracted wavefront. Okay. So look at this. This is the incident wavefront. This is the refracted wavefront. Suppose look at this. This angle R, whole angle 90 degrees. So 90 minus R. So this is the R. Look at this angle of incidence I. This is the 90 minus I. So this is also I because this is perpendicular and this is perpendicular. Okay, understood? So a wavelet takes the same time to reach from A to E as time taken by wavelet at B to reach the D. So look at this. Here BD is equal to C1 into T and A equal to AE equal to, this is the C2 into T, where T is the time taken by wavelet to reach from A to E and B, or B to D. Okay. Now look at this from triangle. Look at this from triangle ABD. Sine I. Look at this perpendicular BD, hypotenuse AD. So this is the BD by AD. Now from triangle AED, look at this from triangle AED, sine R. Look at this. This is the angle. So this is the perpendicular. This is the hypotenuse. So look at this. This is the AE by AD. So here sine I divided by sine R. This equal to BD by A. Now what is BD? BD equal to C1 into T. A equal to C2 into T. So look at this, here C1 into T divided by C2 into T. So C1 by C2, that is, look at this, C1 by C2 means 1 mu 2, that is Ri of medium 2 with respect to 1. Understood? This is the Snell's law. Now first law, so look at this, AS, N and AE are on the plane of the board, so they are coplanar. Understood? Now ncert numerical. Now look at this, a light of wavelength 589 nanometer incident from air to water surface. Now what will be the wavelength, frequency and speed of light of reflected and refracted rays? Okay, for reflection, the wavelength, frequency and speed of light remains same. Okay, now for refracted rays, in refraction the frequency remains same. So frequency in air is equal to frequency in water. Now lambda, look at now speed of light. Look at this, we know mu equal to C by C dash. So C dash equal to C by mu. C is equal to 3 into 10 to the power 8 divided by, this is the almost 4 by 3. Okay, so this is the 9 by 4 into 10 to the power 8 meter per second. So this is the 2.25 into 10 to the power 8 meter per second. Okay, understood? Now lambda, as mu equal to C dash by C, so from this relation we can write nu lambda by nu lambda dash. Look at this, nu cancel out, therefore lambda dash from this relation, look at this, from this relation lambda dash equal to lambda by mu. So here look at this is 589 divided by 4 by 3, so almost 444 nanometer. Okay, understood? Now next, now ncert 10.3, the area of glass medium is 1.5. We have to calculate the speed of light in glass medium. Now the velocity of light is independent of color of light? No. Now next question, will velocity of light is independent of color of light? Which color have greater velocity in the glass, violet or red? Okay, what is the relation of velocity with mu in different medium? Now look at this, mu equal to, this is the C by C dash, where C is the speed of light in vacuum and C dash is the speed of light in that medium. So look at this, here C dash equal to C by mu. So this is the 3 into 10 to the power 8 meter per second divided by 1.5. So this is the 2 into 10 to the power 8 meter per second. Okay, now will velocity of light depends on color? We know the Ri, now look at this, we know the mu depends on wavelength of light, where mu equals to lambda by lambda dash. That is, as Ri of a medium depends on color of light, so speed of light is also depends on color of light. Look at this, here lambda violet less than lambda R. So Ri of violet, for a glass greater than Ri of red. So speed of violet light in glass is less than the speed of red light. So look at this, here CV less than CR. Okay. Now Doppler effect in light wave. In sound wave we know, when a source moves away from the observer, its frequency appears to decrease from the original frequency. Okay, in the same way, when a source of light moves away from us, the frequency of the light wave will be decreased. Therefore, wavelength of light increase If increase of wavelength be delta lambda due to velocity of sources be v away from us, then delta lambda by lambda, this equal to velocity of the sources divided by speed of light. The velocity away from us is taken as positive. So look at this here, wavelength of light coming from a star which moves away from us increases. So the spectrum, so midpoint of the spectrum from this star or this source is shifted towards a red region. So this is known as a red shift. If the sources moves towards us, here V negative, so lambda decreases, so wavelength decreases, therefore this delta lambda is called blue shift. As red shift is the common phenomenon, so our universe is expanding one. Understood? Now a numerical relating to Doppler's effect. Now hydrogen alpha line emitted by a star have wavelength 6563 angstrom. Now the red shift observed is 15 angstrom. What is the speed of the star moves away from us? Look at this, we know the red shift delta lambda by lambda is equal to V by C. So look at this, V equal to delta lambda by lambda into C. Now delta lambda is 15 angstrom, this is the 6563 angstrom, and this is the 3 into 10 to the power 8 meter per second. Now this becomes 6.9 into 10 to the power 5 meter per second. Okay, understood? Now next, now interference. Suppose two sources S1 and S2 send out light wave in all directions. They have same frequency, constant phase relation and equal and almost equal amplitude. So look at this, these waves are superposed in the medium. These waves superposed in the medium. Due to superposition, the intensity at particular point is maximum and another point is minimum, maximum and minimum. Look at this point maximum, minimum, and other point is somewhere between maximum and minimum. So this phenomenon of non-uniform, distribution of intensity of resultant light is known as interference. There are two types of interference, constructive interference. There are two types of interference, constructive interference and destructive interferences. Okay? The phenomenon of producing maximum intensity is known as constructive interference. Suppose consider this point. Here path is the S2P and path is the S1P. Now S1P path is more than S2 path. This path difference, look at this path difference is even multiple of lambda by 2, then constructive interferences occur. Look at this point have path difference even multiple of lambda by 2, okay, or phase difference is even multiple of pi. Now destructive interference, the phenomenon of producing minimum intensity of interference pattern is called destructive interference, and it occurs if this path difference is odd multiple of lambda by 2 or phase difference is odd multiple of pi. Okay, now sustained interference. If the position of maxima and minima of intensity are remain same all the time, then this is called sustained interference. What is the conditions of sustained interference? The two sources send out light wave continuously. Number 1 point. Number 2 point, they must have same frequency. Number 3, they must have constant phase difference. Number 4, they must have equal or almost equal amplitude. Okay? Now number 5, the sources are close to each other. Number 3, the sources are narrow. And number 4, the sources S1, S2 must have same state of polarization. Okay? The sources which obey above conditions called coherent sources. So coherent is very important for interference. Okay? Now the definition of coherent source. Very simple. The two sources having same frequency, constant phase difference, equal or almost equal amplitude are called coherent sources. Now production of coherent sources. Look at this. If S1 in young double slit experiment, this S1 and S2 are produced from same monochromatic source and kept at same distance from S1 and S2. Understood? Next, in Lloyd's mirror, look at this. In Lloyd's mirror, a source and its image formed by the mirror act as a, look at this, and its image formed by the Lloyd's mirror act as coherent source. So this and this are the coherent source. And in Fresnel biprism, look at this. This is the monochromatic source. The image formed by the biprism S1 and S2 are act as the coherent sources. Understood? Now next. Now Young's double slit experiment, simply known as YDSE. Look at this. This is the source and this is a single slit. So light from monochromatic source passes from a single slit, then two slits. Suppose this is the S and this is the S1 and S2. These two slits are identical, so intensity of two sources becomes same. As they are produced from the same source, so they have same frequency, and S1, S2 are equidistant from S, so they have constant phase difference. Okay? Now this is the screen. Now sources from S1, S2 spread light in the medium and they superpose on the screen. Minimum and maximum intensity of interference pattern. Now look at this in this way. Okay, this is shown here. Look at this. This is the maxima. Okay, the line represents the maxima, and between the two lines there is a minima. The fringes are more clear if S1 and S2 are close to each other, and distance of screen from the S1 and S2 is made large. Okay, now there is important points of Young double slit experiment. If any one of source S1 and S2 are closed, no interference pattern is observed because a single source cannot produce interference pattern. If two different sources are placed at S1 and S2, what happens? Look at this. Two different sources have different frequency, so their phase changes continuously, so phase difference is not constant, so interference is not observed. Only general illumination is observed. So at any point on the screen, the intensity becomes 2I0, where I0 be the intensity produced by sources S1 and S2 each. Now what happens if two identical but different sources placed at S1, S2, that is sodium light and sodium light, Here frequency same, but initial phase is not constant. That is why interference is not occurred. Okay. Now, so interference is only produced if they are produced from the same source. If as laser are highly coherent, only two laser beam produces interference. Okay. Now theory of interference. Okay. Suppose this is the sources. S1 and S2. These sources produces interference pattern on the screen S. Okay. At the point P, they meet. Okay. Now the equation of the wave sent by F source S1 and S2 are given by Y1 is equal to A1 sine omega t, where A1 is the amplitude of the wave and omega is the frequency of radius, and omega is the frequency of the wave. Now Y2 is equal to, this is the A2 sine, this is the omega t plus phi, where phi is the phase difference at the point 2 of two waves coming from S1 and S2. A2 is the amplitude of the wave coming from the source A2. Okay. Now from principle of superposition, the equation of resultant wave y equal to, this is the y1 plus y2. So this plus this. Now look at this. This is the A1 sine omega t plus A2 sine omega t plus phi. So A2 sine omega t cos phi plus A2 cos omega t into sine phi. Okay. Now look at this. Here sine omega t and sine omega t. So look at this. A1 plus A2 cos phi into sine omega t plus A2 sine phi into cos omega t. Okay. Understood? Now look at this. This is the coefficient of sine omega t and this is the coefficient of cos omega t. So amplitude of resultant wave due to superposition, this equals to root under of this square plus this square. So look at this. This is the A1 plus A2 cos phi whole square plus A2 sine phi, this is the whole square. Okay. Now look at this. This is the A1 square plus 2A1 A2 cos phi plus A2 cos square phi plus A2 sine square phi. Okay. So look at this. A becomes root under of A1 square plus A2 square plus 2A1 A2 cos phi. Okay. Therefore A square equal to, look at this, this is the A1 square plus A2 square plus 2A1 A2 cos phi. This is equation number 1. Now intensity at the point P is directly proportional to the square of resultant amplitude. That is, look at this, I, that is I proportionate A square. So here I equal to K A square. Now look at this. So I equal to, this is the K square, that is K A1 square plus K A2 square plus 2 A1 A2 K cos phi. So look at this. I becomes, this is the I1, this is the I2 plus 2 root under of I1 I2 cos phi. Okay. This is equation 2. Okay. Now if I1 equal to I2 equal to I0. Look at this. Here I equal to, this is the I0 plus I naught plus 2 into root under of I naught into cos phi. So look at this, this is the 2 I naught plus 2 I naught, this is the cos phi. So look at this, 2 I naught into 1 plus cos phi. From here 2 I naught into 2 cos square phi by 2. So here I equal to, this is the 4 I naught cos square phi by 2. Okay, this is equation number 3. So we get 3 equations. Look at this. This is the square of amplitude, this is the intensity, and this is also intensity when intensity from the two wave is same. Okay, now special cases. Now for constructive interference, the phase difference is even multiple of pi, that is 0, 2 pi, 4 pi. We know cos 0 or cos 2 pi equal to 1, and here cos pi equal to minus 1, so minus 1 square, that is 1. So look at this, here A max becomes A1 plus A2, because look at this, here A1 square plus A2 square plus 2A1 A2, so this square, therefore the under root is omitted. Now look at this, here cos phi 1, so look at this, this becomes root under of I1 plus root under of I2 whole square. This is the I max. Okay, now here look at this, I max, this is the minus 1 whole square. So look at this, here I max is equal to 4 I naught. Okay, understood? Now for destructive interference, phase difference is odd multiple of pi, that is phase difference is pi, 3 pi, 5 pi, dot dot dot. So look at this, here minus 1, here minus 1, and this is the 0. So look at this, A mean, look at this, A mean becomes, this is the A1 minus A2, and I mean, look at this, this is the root under I1 minus root under I2, this is the whole square, and now this is the 0. So look at this, here I mean equal to 0. Okay, so look at this, here A max divided by A mean, this equal to A1 plus A2 divided by, this is the A1 minus A2. Okay, now next, here I max divided by I mean, this equal to root over I1 plus root over I2 whole square divided by root over I1 minus root over I2, this is whole square. Okay, understood? Now if the sources are incoherent, the resultant intensity becomes, look at this, the average value of this. Now average value of cos square phi is half. So for two incoherent sources, the resultant intensity become 4 I naught into half, because the average value of cos square phi is equal to half. So this is the 2 I naught. So for incoherent sources, the intensity throughout the screen is 2 I naught, but for interference pattern, maximum is 4 I naught and minimum is 0. So conservation of energy is valid here. Look at this, here 0 plus 4 I naught equal to 4 I naught, and here I naught, here 2 I naught plus 2 I naught equal to 4 I naught. Okay, now a numerical of ncert. Now look at this, ncert numerical 10.5. In YDSE, the wavelength of light used is lambda. When path difference of two waves coming from the source S1 S2 be lambda, the intensity on the screen be k. When path difference is lambda by 3, what is the intensity? When path difference is lambda, the phase difference phi equal to 2 pi x by lambda. So this is the 2 pi. What is x? X is the lambda by lambda, that is 2 pi. Now intensity at any point is 4 I naught into cos square phi by 2. Okay. Now here phi equal to 2 pi. So phi by 2 is pi. Cos pi equal to minus 1. Now minus 1 whole square. This equal to 4 I naught into minus 1 whole square, that is 4 I naught. Therefore here k equal to 4 I naught. Now what is the phase difference when path difference is lambda by 3? Look at this. Here phi equal to 2 pi. This is the lambda by 3 by lambda. So 2 pi by 3. Okay. Now I2 becomes, look at this, 4 I naught into cos square phi by 2. Now phi equal to 2 pi by 3. So phi by 2 equal to pi by 3. So look at this. This is the 4 I naught into cos square. This is the pi by 3. So this is the 4 I naught cos square pi by 3. That is the half whole square. That is 1/4. So look at this. This is the 1 by 4. So look at this. This is the I naught. Now 4 I naught equal to k. So I naught becomes k by 4. Okay. Understood? Now next. Now we have to calculate the path difference at the point P of the two waves coming from the slit S1 and S2. The distance between the two sources is small d. It is almost equal to 1 millimeter. And distance of the screen from the sources is capital D. It is almost equal to 1 meter. So here capital D is greater than small d. Okay. Now from figure, look at this S2P whole square. Look at this S2P whole square, because this square plus this square. Now this is the y, so this is the, and this is the d by 2, so this is the y plus d by 2. So look at this. This is the d square plus, this is the d square plus y plus d by 2 whole square. So this is the d square plus y plus d by 2 whole square. Okay. Now what is the S1P? Look at this. D square plus d square. This is the y minus d by 2. So look at this. This is the d square plus y minus d by 2. This is whole square. Okay. Now look at this S2P square minus S1P square. This equals to y plus d by 2 whole square minus y minus d by 2 whole square. So this becomes 4 into y into d by 2, that is 2y small d. Now this is the a plus b into a minus b. So look at this S2p minus S1p path difference. This is the 2y small d divided by S2p plus S1p. Now as capital D greater than small d, so this is d and this is also d. So this is the 2yd by d plus d. So this is the y small d by d. So path difference at the point P of two waves coming from S1 S2 is y small d by capital D. Now we have to calculate the position of interference maxima and minima. Okay. Now for maxima, the path difference is even multiple of lambda by 2. So this path difference is equal to this path difference. Therefore, y small d by capital D, this equal to n lambda. So y equal to n lambda capital D by small d is the distance of nth maximum from the center of the screen. Okay. Now look at this. For first maximum, y1 equal to lambda d by d. For second maximum, y2 equals to 2 lambda d by d. So look at this. The distance between two maxima is lambda d by small d. Okay. For minimum. If y dash be the distance of minimum from the center of the screen, then path difference y dash small d by capital D is the odd multiple of lambda by 2. So look at this, this is the 2n minus 1 into lambda by 2. So look at this, y dash equals to 2n minus 1, this is the lambda d divided by 2d. Okay, now from this condition, look at this, for first minima n equal to 1, so look at this, y1 dash, this is the lambda d by 2d. For second minima, y2 dash equals to 3 lambda d by 2d. Now distance between two consecutive minima, this minus this, so this is also lambda capital D by small d. Okay, now fringe width. The distance between two consecutive minimum or maximum is called fringe width. Therefore, fringe width beta equal to, look at this, n lambda capital D by D minus n minus 1 lambda capital D by D. So look at this, beta equals to lambda D by D. Okay, if whole arrangement of YDSE is immersed in a liquid of Ri mu, then wavelength lambda dash becomes lambda by mu. So in this case, beta dash equals to lambda dash capital D by D, that is lambda d by mu into small d. So this is the beta by mu. So beta dash equals to beta by mu. So fringe width in water decreases. Okay, understood? Now next. Now angular fringe width. We know fringe width is lambda capital D by small d. So angular fringe width theta is beta by capital D. So this is the lambda by small d. So angular fringe width depends on wavelength and distance between the two slits. Okay. Now next. Look at this. If a thin transparent slab of thickness T and Ri mu is placed in front of a source, then additional path difference T into mu minus r occurs in this path. So phase difference 0 is not occur at the center of the screen. Due to this additional phase difference, the central phase shifted, suppose this position. If this is the y double dash, then look at this, y double dash d by d, this equal to t into mu minus 1. Therefore shift of central fringe y double dash, this is the t into mu minus 1 capital D by d. Okay, now look at this from here, t into mu minus 1 by lambda into lambda d by d. Look at this, this is the beta. So number of fringe cross the center, this equal to, look at this is the beta, so this is the t into mu minus 1 divided by lambda. Okay, understood? Now next, what happens if white light is used in Young double slit experiment? Look at this, if white light is used in Young double slit experiment, the all color of white light meet at the center of the screen with zero phase difference. Therefore, the central fringe becomes white and other fringes becomes color. Immediate to the central fringe, this becomes red fringe, then other fringes occur. So white, this is the red, this is also red, and this is other color of viv0. Okay. Now next, some important question. What happens on fringes if capital T increases? That is, distance of the screen from the slit increases. Look at this, the fringe with beta equals to, this is the lambda d by small d. As d increases, so fringe with beta decreases, therefore fringe becomes more bright. Okay, if a source is replaced by another source having less lambda, So look at this, here fringe with beta is equal to lambda capital D by small d. As lambda decreases, so fringe width becomes smaller. Okay? Now see, if D increases, look at this, if D increases, here fringe width also decreases. Okay? Now source slit is moved towards S1, S2. Now look at this, if this is the source, if this is the two slit S1, S2 and this is the source, if this distance is capital S and width of it is delta S, now for condition of interference delta S by S, this should be less than lambda d by d. If S decreases in such a way, if this condition obeyed, then interference pattern is observed. If this is not obeyed, interference of different part of the source overlap each other and no fringes are formed. Okay? And in the case if D increases in such a way, if this condition is not held, then no interference pattern observed, because the interference pattern of different part overlap with each other and general illumination takes place. Okay? Now width of the source slit is increased. Look at this, if delta is increased, if this condition should be satisfied. If this condition is satisfied, then interference fringes observed. If not satisfied, then general illumination takes place. That is different point of the source produces interference pattern overlap with each other and no interference fringes are observed. Now if a monochromatic light is replaced by white light, if white light replaces the monochromatic light, all the color VGO meet at the center of the screen with zero phase difference. So central fringe becomes white and other fringes become colored starting from red to violet in either end of the central fringe. Okay? Now example 10.3 of ncert. Look at this. The two slits are placed at a separation of 10 to the power minus 3 meter and screen is placed 1 meter away from the slits. The wavelength of light used is 500 nanometer. We have to calculate the fringe width. Now look at this. What is the formula of fringe width? Look at this. The formula of fringe width beta equals to, this is the lambda capital D by small d. Look at this, here lambda equal to 500 into 10 to the power minus 9, capital D 1 meter, and this is the 10 to the power minus 3. So look at this, this is the 5 into 10 to the power minus 4. So this is the 0.5 into 10 to the power minus 3 meter, that is 0.5 millimeter is the fringe width. Okay, next. Now ncert 10.4. In YDSE, small d equal to this, capital D equal to 1.4 meter. The fourth bright fringe obtained at a distance 1.2 into 10 to the power minus 2 meter from the center of the screen. We have to calculate the lambda. Now distance of nth bright fringe from the central fringe, this is the n lambda capital D by small d. So this is the 1.2 into 10 to the power minus 2 into n4, this is the lambda d 1.4, and this is the 0.28 into 10 to the power minus 3. Now this and this by 5. Okay, so look at this, this is the 20 lambda, this equals to 1.2 into 10 to the power minus 5. So this is the 12 into 10 to the power minus 6. Therefore lambda equal to 12 by 20 into 10 to the power minus 6. So this is the 0.6 into 10 to the power minus 6. So this is the 6 into 10 to the power minus 7. Therefore lambda equal to 6 into 10 to the power minus 7 meter, that is 600 nanometer. Okay, understood? Now next, look at this ncert 10.6. In YDSE, the two color of wavelength 650 nanometer and 520 nanometer are used. First question, what is the distance of third bright fringe of first color from the central fringe? And number two question, find the minimum distance from the central fringe where bright of this and this coincides. Here capital D and small d are not given, so we assumed capital D equal to 1 meter and small d equal to 10 to the power minus 3 meter. Okay, now first question. So first of all, look at this y3. Now y3 equal to, look at this is the 3 lambda capital D by small d. Look at this, 3 into 650 into 10 to the power minus 9 into 1 divided by 10 to the power minus 3. So look at this, 3 into 0.65 into 10 to the power minus 3. Okay, so this is the 1.95 into 10 to the power minus 3 meter is the distance of third bright fringe from the central fringe. Okay, understood? Now next, we have to calculate the minimum distance from the central fringe where bright fringes of this and this color are coincide. Now consider mth order of lambda 1 coincides with nth order of lambda 2. So look at this is the y equal to m into 650 into 10 to the power minus 9 capital D by small d. This equal to n into 520 into 10 to the power minus 9 into 1 into d by small d. So look at this equal to this. So look at this here, m by n, this equals to 520 by 650. So this is the 4 by 5. Therefore fourth order of bright of first equal to fifth order of bright of second coincides. In the same way, 8th order of first and 10th order of second coincides. So for minimum distance, m is taken as 4. So look at this, the minimum distance 4 into lambda, this is the 650 into 10 to the power minus 9, and this is the 1 divided by 10 to the power minus 3. So this is the 4 into 0.65 into 10 to the power minus 3 meter. So this is the 2.6 into 10 to the power minus 3 meter. So this is the 2.6 millimeter. Okay, understood? Now next. Now ncert 10.6. The wavelength of light used in YDSE is 600 nanometer. The angular fringe width is 1 degree, that is pi by 1800 radian. We have to calculate the separation between two slits. Now the angular fringe with theta equals to beta by d. So look at this, theta equals to beta by d, this equal to lambda by small d. Now here theta equal to pi by 1800 and lambda equals to 600 into 10 to the power minus 9 divided by d. Therefore d equal to 1.8, 0.6 divided by pi into 10 to the power minus 3 meter. Okay, this is the 3.4 into 10 to the power minus 3 meter. Okay, understood? Please like, share and comment on this. Now H.C. Verma sum number 18 of wave optics. Now look at this. A thin transparent sheet of thickness 0.02 into 10 to the power minus 3 meter and Ri 1.45 is passed at one slit of YDSE. The amount of light transmitted from this is 4 by 9 of original. We have to calculate the ratio between minimum and maximum intensity of interference pattern. And we have to also calculate number of fringes crosses the center of the screen. So this is the y by beta equal to 2 into mu minus 1 by lambda. Okay, now here number of fringes crosses the central fringe is equal to t into mu minus 1 divided by lambda. So look at this, this is the 0.02 into 10 to the power minus 3, and this is the 1.45 minus 1 divided by lambda is equal to 600 nanometer. Okay, so look at this, this is the 600 into 10 to the power minus 9. So look at this, 0.02 into 0.45 into 10 to the power 6 divided by 600. Okay, now look at this, this is the 2 into 45 into 100, this divided by 600. Now this and this cancel out. Okay, now look at this is the 3 and this is the 15. Okay, so number of fringes crosses the central fringe, this equal to 15. Okay, now next I max by I min. Look at this, I1 equal to I and I2 equal to this. So look at this, this is the I max and this is the I min. Here root over I plus root under of 4 by 9I divided by root over I minus root over of 4 by 9I whole square. So this is the 1 plus 2 by 3 divided by 1 minus 2 by 3, this is whole square. So look at this, this is the 5 by 3 and this is the 1 by 3. So ratio is 25 by 1. Understood? Look at this, HC Verma 31. In YDSE, the wavelength of light used is 500 nanometer. Capital D equal to 1 meter and small d equal to 10 to the power minus 3 meter. We have to calculate the minimum distance from the center of the screen where intensity become half of maximum intensity. Now look at this, we know I equal to, this is the 4I naught, this is the cos square phi by 2. Now maximum intensity is 4I naught, so I becomes, look at this, half of, this is the 4I naught. So look at this, this is the 2I naught. Now I naught here, so this is the 2I naught, this equal to 4I naught and this is the cos square phi by 2. From this condition we can write this is the cos phi by 2 equal to 1 by root 2, that is cos 45 degree. So phi by 2 equal to pi by 4, therefore phi equal to, this is the pi by 2. Okay, understood? Now we have to calculate the path difference corresponding to phase difference pi by 2. So look at this, we know phi equal to, this is the 2 pi x by lambda, where x is the path difference. So here pi by 2 and this is the 2 pi x by lambda, pi cancel out. So look at this, x equal to, this is the lambda by 4. Now the path difference in terms of y in YDSE, this equal to y d by capital D and this is the lambda by 4. From here this y equal to lambda capital D by 4 small d. Now lambda is the 500 into 10 to the power minus 9, d equal to 1 divided by 4 into 10 to the power minus 3. So look at this, this is the 0.5 by 4 into 10 to the power minus 3. So this is the 0.125 into 10 to the power minus 3 meter. Therefore minimum distance from the center of the screen where intensity is half of maximum intensity is 0.125 into 10 to the power minus 3 meter, that is 0.125 millimeter. Okay, now diffraction. The bending of light over a sharp obstacle is called a diffraction. The the size of the edge is comparable to the wavelength of light. Now look at this. Suppose an wavefront incident here. Now light from the wavelets near the edge superpose at the dark region and produces interference maximum and minimum. Okay, so diffraction is produced due to wave coming from two wavelets of a same wavefront. Look at this, where number of sources be large, then diffraction occur. Where number of sources be 2, then interference occurred. Now there are two types of diffraction, Fresnel's diffraction and Fraunhofer diffraction. In Fresnel's diffraction, the distance between source and obstacle or source and screen are finite. So incident wavefront may be plane or cylindrical. And in Fraunhofer diffraction, the distance between source and screen or source and obstacle are infinity. So incident wavefront must be plane. Okay. Now single slit diffraction. Now Fraunhofer single slit diffraction. Suppose this is a monochromatic source. It is placed at the focus of a convex lens L1. So the refracted ray must be parallel. Therefore, the incident wavefront on the single slit is plane. The most part of the incident wavefront undiffracted and forms the central fringe at the point C. Now, very small part is diffracted by an angle theta. If A be the width of the slit, then the path difference between two extreme points of the plane wavefront is the A sin theta. Okay? Now look at this. If the path difference is A sin theta is equal to lambda, then path difference between this point and midpoint is lambda by 2. And look at this point and corresponding point of next half is also lambda by 2. So look at this, the two wavelets from this point to this point cancel at the point P. In the same way, all the point of this half cancel out by the other corresponding point of the other half. So at the point P is minimum intensity occurred. So condition of minima is, look at this, this is the A sin theta equal to n lambda, where n is the order of the minimum. Now for first minima, this is the A sin theta equal to lambda. Okay, now for nth minima, look at this, A sin theta equal to theta, this is the n lambda, so theta equals to n lambda by A. Now if this is the capital D and now distance of P from the C is y, then theta equal to y by D. So look at this is the n lambda by A. So look at this, y equal to n lambda D by A is the distance of nth minimum from the center of the screen. So for the first minimum, look at this, from this point, this is the, look at this is the lambda D by A. For second minimum, look at this, from this to this is the 2 lambda D by A. In the same way, from this to this, lambda D by A, and from this to this is 2 lambda D by A. So distance between two consecutive dark is equal to lambda D by A. Now look at this, if A sin theta, this equal to 2n plus 1 into lambda by 2, then maximum, then secondary maximum occur. Look at this here, A theta, this is 2n plus 1 into lambda by 2. So look at this here, theta equal to 2n plus 1 into lambda by 2a. Now where now we know theta equal to y by capital D. So this is the 2n plus 1 into lambda by 2a. Now here, so y equal to 2n plus 1 into lambda d by 2a. For first secondary maximum from this to this point, look at this, n equal to 1, so y becomes 3 lambda d by 2a. Now for secondary maximum, look at this, n equal to 2, so this becomes 5 lambda d by 2a. Now distance between two consecutive maximum, this is the 5 lambda d by 2a minus 3 lambda d by 2a. So look at this, this is the lambda d by a. So distance between two consecutive minima and distance between two consecutive secondary maximum are same. Now width of central maximum, look at this, the central maximum extend on either side by the first minimum. Now for central maximum, angular width theta naught equal to 2 theta, that is, this is the 2 lambda by a. Therefore, so beta naught becomes, look at this, 2 lambda d by, so look at this, width of central maximum is twice the fringe width of diffraction pattern. Okay, now next. Now an important question. If the width of the slit becomes half, what will be the intensity of central maximum? Now the angular width of central maximum theta naught equal to 2 lambda by a. When a becomes half, the angular width of central maximum be double, and amount of light energy falling on the screen simultaneously becomes half. So half light energy falls on double area, so intensity becomes 1/4. Now if width of the slit becomes double, then angular width becomes half. Simultaneously, the amount of light energy becomes double. So double light energy falls on half area, so intensity becomes 4 times. Okay. From our discussion, we can distinguish between diffraction and interference. Look at this. In diffractions, the width of bright bands are not equal. But interference, the width of bright band may equal. The intensity of bright band in diffraction pattern is not equal, but in interference, the intensity of bright bands are equal. In diffraction, dark bands are completely dark, but in interference, dark band may not completely dark. Okay? The diffraction is produced due to superposition of two waves coming from the same wavefront, but interference is produced due to superposition of two waves coming from two coherent sources. Okay, now a numerical. Look at this. In a single slit diffraction, the wavelength of light used is 500 nanometer. Distance of the screen is 1 meter from the slit, and first minima is obtained at a distance of 2.5 into 10 to the power minus 3 meter. We have to calculate the width of the slit. The distance of first minima from the central fringe y1 equals to lambda d by a. Look at this, y1 is equal to 2.5 into 10 to the power minus 3 meter. So this is the 2.5 into 10 to the power minus 3. Lambda, this is the 500 nanometer, that is 500 into 10 to the power minus 9. D 1 meter, and this is the a. So look at this, a equals to 5 into 10 to the power minus 7 divided by 2.5 into 10 to the power minus 3. So look at this, this is the 0.2 into 10 to the power minus 3. Therefore, width of the slit is equal to 0.2 into 10 to the power minus 3 meter, that is 0.2 millimeter. Okay, understood? Now next. The width of the aperture is 4 into 10 to the power minus 3 meter. Wavelength of lambda is equal to 500 nanometer. Find the distance at which ray optics valid. Now ray optics valid means the distance at which maximum deviation is equal to edge of the obstacle. So look at this. This is the lambda ZF by A. This equal to A. Therefore, look at this. ZF is equal to A square by lambda. Here A equal to 4 into 10 to the power minus 3 whole square, and lambda is equal to 400 nanometer, that is 10 to the power minus 9. 16 into 10 to the power minus 6 divided by 4 into 10 to the power minus 7. So look at this. This is the 40 meter. So distance up to which the ray optics valid, this is the 40 meter. Then after 40 meter, the bending of light is equal to edge of the obstacle. Okay. Now next. Now look at this numerical. What should be the width of each slit of YDSE be to obtain the 10 maxima of double slit pattern within the central maxima of single slit pattern. Now look at this. Suppose this is the central maxima. Okay, its angular width is 2 lambda by A. If 10 maxima is obtained here, look at this. So the figure is like this. The angular width of each maxima of YDSE is equal to lambda by D. So for 10 maxima, the angular width is 10 into lambda by D. Now 10 into lambda by D is lies within the central maxima. So 10 maxima of YDSE lies within the central maximum of single slit pattern. So this equal to this. So this is the 2 into lambda by A. Here A is given, we have to calculate D. Look at this, this and this cancel out. So D becomes 5 into A. Now A is equal to, look at this, 0.5 millimeter. So 5 into 0.2 mm. So this is the 1 millimeter. Okay. So width of each slit of YDSE is equal to 1 millimeter. Understood? Now next. Now look at this resolving power. Look at this. If two objects are like this, okay, so they are not separated each other, so they are not resolved. Now look at this. If these two objects are appear like this, so they are just resolved. Now two objects are appear like this, so they are well resolved. Okay, the minimum linear or angular separation between two close objects at which they appear just separated when viewed through an optical instrument is called limit of resolution. The reciprocals of limit of resolution is called resolving power. Now limit of resolution of compound microscope. The minimum linear separation between two close objects at which they just appear separated when viewed through a microscope is called limit of resolution, and this limit of resolution is equal to lambda divided by 2 mu sin theta, where mu is the Ri between the lens and object, theta is the angular separation between this, and lambda is the wavelength of light used. Now the resolving power of microscope Rp equal to 1 by D. So this is the 2 mu sin theta divided by lambda. So look at this, as resolving power is directly proportional to mu, so a microscope of oil immersion objective has greater resolving power. Now the resolving power for violet is greater than resolving power for red light, and greater the aperture of the objective, greater the resolving power. Okay, as electron wave has very small wavelength, so electron microscope has greater resolving power. Okay, now limit of resolution of a telescope. The angular separation between two close objects at far distance at which they just appear separated when viewed through telescope is called limit of resolution, and limit of resolution delta theta equal to, this is the 1.22 lambda divided by d, where d is the diameter of the aperture of the objective. So resolving power of telescope rp equal to, this is the 1 by delta theta, and this is the d divided by 1.22 lambda. So look at this, greater the aperture of the objective, greater is the resolving power. Smaller the wavelength, greater is the resolving power. Now ncert example 10.6. Now the diameter of aperture of the telescope is 100 inch, that is 100 into 2.54 divided by 100 meter, that is 2.54 meter. The wavelength of light used is 6000 angstrom. We have to calculate the limit of resolution of the telescope. Now look at this, the limit of resolution of the telescope delta theta, this is the 1.22 lambda by d. So this equal to 1.22 into 6000 into 10 to the power minus 10, this divided by 2.54. Now this equal to 2.9 into 10 to the power minus 7 radian is the limit of resolution of the telescope. Okay. Now polarization of light. We know that light is an electromagnetic wave. It has electric field vector and magnetic field vector. Look at this, here electric field vector, which is responsible for light, is vibrates this direction. Okay, and magnetic vector vibrates along z axis, and direction of propagation is directed along x axis. That is, vibration of wave are different plane. Now polarization, the phenomenon by which the vibration of light wave is restricted in a particular plane is called polarization. Now look at this, electric field vibrates normal to this line, and magnetic field vibrates normal to this plane. Okay, this is the tourmaline crystal. When unpolarized light passes through the tourmaline crystal, only light wave travels in this direction, and vibration of light wave is directed normal to this line. So this is the polarized light and this is the unpolarized light. In unpolarized light, both electric and magnetic field present, but in polarized light only electric field present. If YDSE be the intensity of unpolarized light, the intensity of polarized light becomes I naught equal to, this is the YDSE by 2. This is known as polarizer. The device which polarized and unpolarized light is called polarizer. Now analyzer, the arrangement which detects what type of polarization it is and what amount of light is polarized is known as analyzer. The intensity of light wave after transmission of analyzer is directly proportional to cos square theta, where theta is the angle between plane of polarizer and plane of analyzer. If I naught be the intensity of incident polarized light at the analyzer, then look at this, I equal to I naught cos square theta. This law is known as law of Malus. That is, intensity of transmitted ray after analyzer is directly proportional to the square of the cosine of angle between plane of polarizer and plane of analyzer. Okay, now discuss the intensity of transmitted ray after the second Polaroid when The third Polaroid placed between two cross Polaroid is rotated. Now cross Polaroid means the angle between the axis of this and this is 90 degree. Suppose angle between this and this is equal to theta. So angle between this and this is the 90 degree minus theta. Now I be the intensity of unpolarized light. So after polarization the intensity becomes, this is the I by 2. Now as the angle between P1 and P3 is theta, so intensity after transmission of P3, this is the I3 equal to I by 2 cos square theta. Again after transmission of P2 the intensity be I2, so I2 equal to I3, so this is the cos square 90 degree minus theta, because angle between P3 and P2 is 90 degree minus theta. So look at this, I2 becomes, this is the I3 means I by 2, so this is the I by 2 into cos square theta into sin square theta, and look at this is the I by 8 to sin theta cos theta whole square. So look at this is the I by 8, this is the sin square 2 theta. Now intensity becomes maximum when 2 theta equal to 90 degree, that is theta equal to 45 degree. So intensity of final transmitted ray I2 is varies from 0 to maximum at the angle of 45 degree, then again decreases to 0 at the angle of 90 degree. Now polarization by reflection. Now look at this, the electric vector vibrates normal to the plane of the board, and electric and magnetic vector vibrates in this direction. Now this is the incident ray. At a particular angle of incidence at the polarizing angle, the reflected ray is completely polarized. This angle of incidence is called polarizing angle or Brewster angle. If IP be the Brewster angle, then reflected and refracted ray becomes perpendicular at this angle. Here IP is the angle of incidence, so angle of reflection is also IP. If R be the angle of refraction, then look at this is the IP plus 90 degree plus R, this is the 180 degree. Therefore R equals to 90 degree minus IP. Now applying Snell's law, mu equal to, this is the sin IP divided by, this is the sin R. So look at this is the sin IP by sin of, this is the 90 degree minus IP. So look at this is the 10 IP. So Ri of the medium is tangent of polarizing angle. This statement is known as Brewster law. Okay. Polaroid is a thin, large crystalline material at which polarization of light takes place. Now use of Polaroid. Polaroid are used in the windscreen of a car. Polaroid is also used in sunglass and film of a 3D picture. Okay. Now numerical. Look at this ncert numerical 10.8. Mu equal to 1.5, we have to calculate the Brewster angle. Now Brewster angle is equal to IP. As mu is given, we can easily calculate the Brewster angle. Now from here, this is the 1.5, so this is the 10 IP. Therefore IP equal to, this is the 10 inverse 1.5, this is almost 56 degree. Okay, so Brewster angle or polarizing angle is 56 degree. Okay, many thanks for watching this video. This video will be extremely helpful for your preparation in board, NEET, main and advanced. Please like, share and comment on the video. And if you are new, don't forget to subscribe my channel to get the new videos of this type. Okay?